Lesson 10 for probability and the multiplication rule. So here we're going to be looking at scenarios that could be independent or dependent events. If events are independent, that means that one event has no bearing on the other. For example, if I flip two coins and say, do they land on heads, 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 tails, tails, heads, or tails, tails? Well, one coin doesn't care anything about what the other coin is doing. So whichever side either one lands on has nothing to do with the other. That would be called independent. Now, dependent, uh, one event does depend on the other. So here I have this box of kitty stamps. And all right, well, they're different colors. So what if I blindfold myself and mix these all in a bag and I randomly pick out one? What's the chance that the first one I pick is yellow? Well, there are 12 stamps and two are yellow, so it'd be 2 out of 12, which would reduce to 1 out of 6. Okay. All right, but let's say I pull this out so I do not replace it. Now I have 11 stamps remaining. And again, blindfolded, they're all mixed in a bag. I have no idea which one's which. And I pick another one. What's the chance that the other one is also yellow? Well, now it's 1 out of 11 because there are 11 stamps remaining and only one of those is yellow, right? So it's 2 out of 12 times 1 out of 11 that they would both be yellow. That I picked the two yellow stamps. And that leads to this notation here. So if dependent, which is what I just described, then the probability of picking yellow and also yellow, right? So like the two yellow kitties here would be the probability that the first event happens multiplied by the probability of B happening given that A happened. Right? And I can write that out here. Let me write out what I just said verbally. Right? So because this notation you gotta see it, think about it a little bit. Right? The probability that they would both be yellow is right this right here. So I'll just point to the probability of A happening was 2 out of 12. Right? There were two stamps out of 12 that were yellow. Could happen. Right? Now once that happens, I can keep on multiplying down the chain here. Right? Because once I take out one, and that was happened to be yellow. Right? Now that that event did happen, the that opens the door for this next possibility to happen. Right now, here this probability of B given A is okay. Well, now that A happened, there are only 11 stamps remaining because I did not replace the first stamp, and only one of those is the yellow kitty that remains. Right, so it'd be like this. So you could say the probability that again, I picked two out of a bag that, as I'm blindfolded, so I have no idea which are which. Okay. And they happen to both be yellow. Well, that'd be 2 times 1 is 2. 12 times 11, I think it's 132, isn't it? Pretty sure. Double check that here. Oops. All right. 12 times 11. Come on here. Yeah, 132. Right. So I could say that they were the 2 out of 132 chance that the two I chose would be both yellow. Okay. And that would be dependent then. Right. Okay, and there's how you read it. Probability of A and B happening is probability of A multiplied by the probability of B given A. Right, that's how you read that notation. All right, so let's jump into book examples. Okay, go through the main examples and then a few from the main chapter. All right, so yeah, they talk about independent events. A compound event is a composite event that of two simple events. If they are independent, that means that the outcome of one does not affect the other. For example, tossing two different coins or spinning a spinner over and over, and one spin has no bearing on the next spin, so like that. You can very simply multiply them together. And so here you go. All right, so if it's independent, probability of A and B is very simply probability of A times probability of B. One doesn't care about the other. Okay. All right, so example one. Anna is a member of a gaming website that randomly pairs users together to solve puzzles. Of the 50 players currently online, Anna is friends with 10 of them. Suppose Anna is paired with a player for a game. Not liking the outcome, she disconnects and is paired again. What is the probability that she is uh, not paired with a friend in either match? Right, so you know that these are independent events because once she disconnects and reconnects, or the reconnection has nothing to do with who was paired with the first time. Right? So there are 50 other people playing this game. She's friends with 10 of them, which means she's not friends with the other 40. Right? So the chance of being paired with somebody who's not a friend the first go round would be 40 out of 50. Right? And when she disconnects and reconnects, well, she could be paired with right? Any of those people again, including the person she was paired with the first time, right? She might just get the same person again, like, hey, I mean, there's a 1 out of 50 that can happen. But the question here, target question is not friends again, okay? So there again, 40 out of 50 should be not friends with. So you multiply this across, this would be 1600 out of 2500. Right, the hundreds you could cancel, this reduces to 16 out of 25. Okay, so 16 out of 25. And if you want that as a percentage, 16 out of 25, well, I can multiply it by 4/4 to bring this up to 100. 16 is 64 out of 100. That looks like I call it 64% as a percentage, right? Or as a decimal, 0.64, right? If you like the decimal version. Okay. So she connects with someone randomly and then disconnects and connects again with somebody randomly. The chance that she was the likelihood that she would be not friends with either of those people would be 64%, if they say it that way. Right. Right. We have this alternate method with this geometry. I like this too. Okay, let's take this because a lot of times you guys are looking at numbers on a page and fractions, but here's a nice visual. Okay? So she's not friends with 4 out of 5. So along the single axis, that would be like 4 blue and 1 pink. So she's friends with the pink, right? Okay? And then if you're going to multiply, you could think about that as a separate axis that's orthogonal, say perpendicular. Okay? And so this entire blue region would be that she's not friends with either, which covers 64%. If she was friends with one but not the other, that's like this pink region plus this pink region. And if she was friends and also friends, well, that's very unlikely. That's just this little gold box right here, which is 1 in 5 times 1 in 5. That'd be 1 out of 25 or 4%. There's a 4% chance she'd be friends with both of them. That's another way to look at it, right? So the same thing we just did. We solved for that blue square is what we solved for. That's this math aligns with this blue square. So that's an interesting way. And let's look at dependent events. Dependent. Okay, so now an outcome does depend on the previous outcome. Classic example is if you have a bag of marbles that are different colors and you're gonna reach in and choose one randomly, or I was using stamps, right? So if these were like all in a bag and I can't see what's what, I just start picking them, right? What's the chance that things will not come, right? But see, like if suppose you have so many red marbles and so many blue marbles, if you draw one out, right, and then you do not replace it, and that's an important aspect, right? If you don't replace it, then you've changed the number of marbles inside the bag, right, including what colors they are, right? The proportions, right? So if you draw a second marble, again, without replacement, then that depends on the first marble you do. Now, if you replace the marble, then it goes back to being independent all over again, because it's like flipping a coin, right? All right, so that leads to, that's where I wrote this notation here. Really, I just wrote this for the dependent case, right? Because this one you have to think a little bit deeper on. The probability of something happening followed by something else is, well, the first event had to happen, and then probability of the second event given the first event, because it shakes everything up, right? If I draw one of these 12 stamps, boom, now I'm down to 11 stamps, and the proportions of all the colors change too, right? So you got to consider all that. All right, so here, let's look here. They have some questions for like, is something independent or dependent, right? So you have to be able to identify that. The spinner is spun twice. Well, if you spin it the first time, okay, it's relatively unlikely that second spin would be affected by the first. I mean, maybe you can make a case, but basically independent. So we're going to basically treat this as independent. In a raffle, one lottery ticket is drawn for first place, and then another ticket is drawn for second place. Well, once you draw the first ticket, as long as you don't replace it, then the second case would be dependent on the first, because now the first guy can't also win second place. Right? Now, if you replaced the raffle ticket, then you're back to the beginning again, and now we're back to independent. Right? So this is probably going to be dependent. Right? You could change the case to make that the opposite. But a random number generator generates two numbers. Yeah, this looks like also independent because the second number would have nothing to do with the first number. All right. So I think the default assumptions here would be independent, dependent, and independent. Right. I think, yeah. Okay. So that's probably what they're looking for. Let's do example 3 here. Probability of dependent events. The pizza that Jose and Tessa are eating has 10 slices and is half cheese, half mushroom. I'd like to draw that out. Let's get that, let's draw that pizza before I keep reading that paragraph. Okay, so example 3, drawn out here. Okay, got a pizza. It says 10 slices. Let's get 10. Okay, so I can definitely cut it in half. 1, 2, 3, 4. There's 5 slices on the right. 2, 3, 4, 5 slices on the left. Okay, now I got 10 slices. It says half. Where is it? Okay, half cheese, half mushroom. So let's call it cheese, 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 cheese. Let's go mushroom, 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 mushroom. Okay. Tessa spins the pizza around. Right, so it's all spinning, right? Got like a giant prize wheel. And randomly selects a slice of okay, happen to be mushroom pizza. All right, so she's gonna randomly choose one. She basically blindfolded, she has no idea. Let's see, say she picks this one right here. Boom. Right. So Tessa has a mushroom slice. Right? After that, so Jose then spins the pizza and selects after that. What's the probability that both he and Tessa select a mushroom? Okay, so well now, see, Jose only has these four slices to choose from to also get a mushroom. Now, out of nine remaining, right? And maybe he does, maybe he picks this one, for example, right? So the chance that Tessa picks a mushroom on the first go round would be 5 out of 10. It's random, right? The chance that Jose then also picks a mushroom, well, now there are only four slices remaining, four mushroom slices remaining out of nine total, right? So I think that the 5 times 4 is 20, out of 10 times 9 is 90, and that could that could reduce to 2 out of 9, right? That they end up both getting mushroom. Is that what your book came up with? Yes, right? And that's exactly how they did it too, right? Probability of mushroom and mushroom is probably a mushroom for Tessa times probability of mushroom for Jose, given that um, Tessa got mushrooms at the first go round, right? So this is probability of B, or sorry, a probability of A happening multiplied by B given A. That's what this is. This is probability of A multiplied by probability of B given A. Right, so you can think of it that way. Right? So because it's a dependent event. This is dependent events. Right? Because Tesla's not putting that mushroom slice back. She likes the mushroom slice. All right, so I got some highlighted here. Let's go through some of these examples. A die is rolled and a penny is flipped. Find the probability of rolling a 2 on the die and landing a tail. Well, that would definitely be independent events because the rolling a die and the flipping a coin have nothing to do with each other. Right? One doesn't care what the other does. Right? So I would like a 2 to show up on the die and a tails to show up here. I'll spell out tails. How about that? Right. Right. Well, so again, if it's independent, probability of A and B is very simply probability of A happening multiplied by probability of B happening. Okay? So for the die, that'd be 1 in 6. For the coin, that'd be 1 in 2. Right. Right. And then altogether, that'd be 1 in 12. Okay. So the probability of rolling a 2 and flipping a tail, that's going to happen 1 out of 12 times. Right. So if I just kept rolling and flipping over and over and over and over, right? Let's say I did that like 120 times, and I would expect that to happen like 10 times because 10 out of 120 would reduce to 1 in 12. All right, so there you go. Got that? Ooh, let me check. That was number 3. Yeah, okay. And then your book says, by the way, this is approximately 8%. I'm looking at the teacher's guide. I don't think it's exactly. Yeah, it's like 8.3. So approximately 8.3%. And you're looking at the decimal version on the calculator, 0.08 in a string of threes. Okay, so about 8. Okay, what do we got next? Reality stories, and they want you to very simply say, is it independent or dependent? So let's go through some scenarios. I think it's pretty valuable to be able to identify that. You roll an even number on a die and then spin a spinner numbered 1 through 5. That sounds independent because the die and the spinner have nothing to do with each other. Number 7, an ace is drawn from a deck of 52 cards and is not replaced. Then a second ace is drawn. Yeah, remember that? I was breaking out the deck of 52 cards. Okay. Well, once you draw one card and you don't replace it, now the number of cards in the deck goes down to 51, right? And the proportions of the cards change. So that would be dependent. Number 8, we've got a bag of 3 green and 4 blue marbles. A blue marble is drawn and not replaced. And the second blue marble is also drawn. Yeah, bags of marbles, you're not replacing them. The second marble you draw depends on the first you draw. Because once you draw the first one, you can't be drawn again. If the number of marbles changes, the whole thing. You roll 2 fair dice and roll a 5 on each. Well, one die doesn't care about what the other die is doing, so that sounds like independent. All right, so there you go. You got independent, dependent, independent. Hopefully you could come up with that. And I would tell you how to do the math to make those calculations. All right, so let's do a couple more examples here. cards, 11 cards. The card is drawn from a deck of playing cards and is not replaced. That already makes me think dependent. So I'll go ahead and spell it out. Dependent. There. A second card is drawn. Find the probability that the first card is a jack of spades and the second card is black. Ooh, ooh, okay. So jack of spades, there's only one jack of spades out of the standard deck of 52 cards. So the chance that you draw that would be 1 out of 52. Okay? Right. Multiplied by, well, the second card is black. Now here's where it gets tricky. I know the jack of spades is a black card. Right? So that removes one of the black cards, doesn't it? Okay? And the remaining cards, there are 51 altogether. But how many black cards? Well, there started out being 26, because there are 26 black and 26 red. But it's no longer the case because we pulled out one of the black cards. There's only 25 cards remaining that are black. So the chance that the second card I draw is black is, well, 25 black out of the remaining 51. So multiply this together. It's got, okay, got 25 out of, and I don't think this will reduce because I know 25 is composed of 5 times 5. That's how it breaks down in terms of primes. And 5 is not a prime factor to either of these numbers. So this will not reduce, right? 26, 52, right? So that's the fraction. Let me see what that is approximately as a percentage. That would be, ooh, and then I'll say times 100 to make this a percentage, 0.94% of the time. So a little less than 1% of the time. What's number 11? Let me check the book, make sure. Yeah, they got exactly this fraction, and they say approximately 1%. At least that's what the teacher's guide says. It says about 1%, which is pretty dang close. That's about it. All right. All right. One more I want to do with you guys. Number 20, travel. A travel agency conducts a survey. I like this one. Right. Haven't solved it yet, but I like this Venn diagram. I'm pretty sure we can do this here. A survey to determine whether people drive or fly to their destinations. And they got a Venn diagram set up. So let's copy that Venn diagram here. Okay. Okay, so we got fly in the circle. We got drive in the circle. Okay. Now there is some overlap. There's an intersection. So maybe you fly part of the way and then you drive a lot of the way too. So there could be an intersection. Right. There could also be a wider universe. You guys remember that? A wider universe, right? Where people neither fly nor drive. Maybe they just like walk to their destination, right? or bicycle or take a train. How about that? Right? Like if you're over in Europe or Asia, maybe you take a train to your destination. Right? Um, Okay, the results indicate that the probability of driving is 60%. Well, it's 0.6. It says 0.6, but you guys know it's 60%. I'm going to mark it this way. I'll put it as a percentage because it is a bit more intuitive. I think 60%. Okay. Now that could be this entire circle. That does not necessarily exclude flying. I don't want to put 60% just in this wedge over here because remember, you could do both flying and driving. Right? So more than likely. Probability of driving and flying. You guys see that upside down U looking symbol? That's an intersection. That means you both have it, right? It says 0.2. I'm going to interpret that as 20%, and actually does go in this wedge right here. Okay, so it's 20% of all vacationers did both flying and driving, or a little bit of both, a little bit of next. Okay? And the probability the family did not vacation at all is 0.1, which is 10%. That goes in this wider universe. So I'll put universe out here, right? And I'll put 10%. So they said 0.1, that's 10%. Okay. Question, what's the probability the family reached their vacation destination by flying? By flying, which could be anything over here. Okay. Well, we got to take these given values and figure out everything else. Okay. So remember how 60% of people drove? But that doesn't necessarily exclude flying. And I know that 20% both drove and flew. That means that 60 minus 20, there must be 40% of people who strictly drove but did not fly, right? Because this 40 and this 20 add up to the total 60 that did drive. Okay. Now, we have almost everything filled out except for the people that strictly flew and did not drive at all. But we can figure that out because I know in the universe has to be 100% of people altogether. 100% of people are all in this universe. Okay. So I have 20 here, 40 here, that's 60, plus this 10 that did not vacation, I guess. Okay. We didn't forget the train. Okay. That's 70. You guys see this adds up to 70%. Well, if that accounts for 70% of people, then this wedge that strictly flew must be the other 30%. So this has got to be 30% right here, doesn't it? Right, now we're up to 100% of people, 100%. Okay. But what was the question again? Reach the destination by flying? Now, if I'm interpreting by flying, I think it's this entire circle. So it could be strictly flying or flying and driving. So I'm going to say that's 50%. So I think A, flying, I'm going to call it 50%. And let me check the teacher's guide to make sure I'm not off base here. That's 20A. Let's flip the page here. 20A, destination by flying. Okay. They're saying 30%. They're saying 30%. Right. Okay. So somehow I'm interpreting the question. Okay. I think I'm interpreting question B is, well, okay. Drives will also uh drives will also okay, right. Um fly. Okay. Well, I'll put 30% book answer. Book answer. And 50% was my answer. Okay. I think it depends how you interpret it, right? Okay. How you interpret it. So they're looking for strictly flying, I guess, like strictly flying. Okay. Only reach the destination by flying. I might put in the word only. Okay. Question B, what is the probability that a family that drives will also fly? Okay. So this is a dependent event. So this is that whole, remember, probability of A and B is A given B or B given or something like that, right? Drives will also fly. Okay, so driving is these two parts here, this 20 and this 40%. Okay. But will also fly, that's this wedge compared to this wedge. Okay, so drives will also fly. Okay. That would be 20% of everybody drives and flies out of the 60% that does drive. Okay, so here's 60% that are driving. Also flying is 20% of, again, everybody. Okay. That reduces to 1 out of 3 or 33.3%. Okay, and let me double check. Your book says the answer, yeah, it says that that's the answer right there. Right, so both your book and I agree on that answer. Okay. All right. And so, yeah, looks pretty good. All right. Boom. All right, so we talked about independent and dependent events, and okay, there you go. That is a wrap on 10-4.